Our next paper today is by Trevor Seifred, Sierra Nevada Corporation, entitled Compatibility with Cost. So with that, let me turn it over to Trevor.
The title of my white paper is Unlocking the Potential of Large-Scale MOSA Integration. So I spoke yesterday more at the ground level of some of the more direct integration challenges that we ran into and some of the ways to solve them. This is kind of zooming out a little bit and a little bit of the background of my history with the standard and what I was working on is I'm a senior software engineer at SNC, and SNC was chosen as the mission system integrator for the Bell 360 Invictus aircraft, which was their entry into the FARA Increment 1 competitive down select. And really the main goal of our development on that program was going towards an event called the Open System Verification Demonstration. So this was a fairly early demonstration prototype to prove how open, how modular our mission system was. So it was a third-party event where they came in and evaluated the system. And in doing that, we had to make a lot of face conformant UOPs and integrate a lot of third-party components. But at the same time, we were also kind of evaluating the airworthiness and kind of the long-term verification strategy for what the system was going to look like. And we kind of came up with some lessons learned and some kind of long-term prospectus on what an actual open system integration would look like, and the value proposition for what it would be down the road once the system was complete. So some background information. There was a GAO report back in 2023 that assessed a lot of major defense acquisition programs, and it found that a lot of them were implementing a MOSA, were still reporting typical program delays, and the net cost of the programs were still increasing. So programs that were implementing a MOSA, they were finding that they were still costing the same or more than a typical federated development program. And so in that case, where is the benefit going to come from in implementing a MOSA? It's really got to come from after the system is developed, after the system is integrated onto the platform, and really future integrations and upgrades and ports of other software rapidly deploying into that platform are really going to realize the benefits. It's supposed to increase the speed at which the time to field of future upgrades happen, because that initial development still has a lot of the same risk challenges, development process, airworthiness. It has to go through all the same processes. And in fact, one of the things that we were kind of analyzing as we were doing this development, this is still pretty early in a program that we were working towards these OSVD events, but we were developing some of our early DO 178 planning documentation for airworthiness, and kind of evaluating how long it took to add a component, add a feature to this system, compared to what it was to add a similar component for previous products that we had made. So we ported some of our old software into this, into our mission system, and we also made some new applications. So we had some numbers and some experiences for making those kind of platforms before. And the first time going through this of making a very large scale modular open platform, especially something as broad and complex as a mission system for a future vertical lift aircraft, it actually it does increase the development time a little bit. At least it did in our case. And when we kind of looked at it, one of the problems was that a lot of our team did not really have a lot of experience with MOSA and with base development, and there is a learning curve definitely in coming up to speed on some of the application there. And so that initial development, there's a lot of other things you have to consider too, like in order for the actual complexity to be mitigated and to make sure that it actually has portability down the road, it does take a little bit extra time. You've got not just the running the face conformance test suite and verifying the conformance of face UOPs, but integrating other software into your system and dealing with any of the integration challenges that I mentioned yesterday. And if some of those things are done incorrectly, if the system is not actually open, even though you might think it is like in a vacuum, it's not going to realize the benefits of applying a MOSA down the road. It might not be as open, and it's very hard to actually quantify whether or not a system is open, as it turns out. And FARO was one of the first opportunities, and the government had to really assess whether or not the system was going to meet its open objectives. And the OSVD event was kind of a trial run in doing that. And I'll talk a little bit more later about what that entailed and what it showed. But on the flip side, even though you may spend a little bit more time doing your initial development, either porting your applications to apply a MOSA or developing them from the ground up, down the road, then you do realize the cost and schedule benefits. If you really deeply understand the computing architecture and the platform that you've developed and the modularity of it and where things can get inserted and added and changed, after that, then the benefits really are realized. And you can even realize those benefits within your own development team for future applications. You can build up kind of an array of tools, of processes that help you speed up the time to development. So what makes it possible for the modularity to occur, and what makes it difficult? What decisions can you make that can actually end up locking out development down the road? So when you're developing an open system, you have to make a series of decisions against competing standards. The standards that FACE and that SOSA call out are open standards, but at some point you have to pick one. You have to pick if you're going to do for example, a POSIX operating system or a ARINC 6x3 operating system. Are you going to do ARINC 6x1 graphics? Or are you going to do OpenGL graphics with a compositor and things like that? And once you kind of lock into that as your open platform and your computing environment, then future upgrades really should use those as well, because then you get to realize the benefits. If you're trying to do a port of something using a different open standard, a competing standard, then you're kind of doing a more of a federated integration anyways, because you're having to write all these porting layers, and it's just like using a different ICD. So once you lock that in, most of the vendors really need to offer a product that meets those same standards. Another problem is that a lot of programs are going to production without verifying if the system meets MOSA objectives. And a lot of the programs that were surveyed in this GAO report didn't really specify a time frame when they were verifying whether or not their system was MOSA, or if they even plan to do so after starting production. They applied the open standards, they might have verified it for their particular system, but there's no way to really know from that point whether or not that in the future it's actually going to be an open platform that other things can deploy to. So it's very hard to determine initially when you're developing that system whether or not the MOSA development is actually a success and it meets its objectives. So looking at the standard, specifically the FACE standard, because I'm focusing more on the software side. It does give a lot of open and agreed upon paradigms when each of the suppliers is developing it. However, there can be some significant differences between what the computing environment is for the integrator and for the supplier. So when say you had a very large program, maybe potentially a deployed program, the standard tends to kind of lock that one particular platform into that version of the standard, and future integrations can be non-conformant or either non-compatible with the integrator's platform. So then I talked about a bit more of that in the white paper that I went over yesterday. But just the very fact that you're implementing this open standard, it adds some additional development requirements, adds a little bit of complexity. There's all these injectable interfaces that you have to apply, for example, and that can make the code a little bit harder to read, harder to maintain, or harder to certify. Specifically in talking about code complexity, like I said, the injectable interfaces, and each of your UOCs has to be instantiated, has to be configured, has to be injected. There's a lot of upfront boilerplate code. One of our UOPs, for example, I was looking at the UOP initialization in main, and there were 1,294 lines of code just in the main where we were initializing the UOCs, injecting them, adding the configuration, starting them up, giving them each other all the pointers to each other. So that's a lot of code, and all that code has to be verified at some point. Now, if you have code coverage requirements for DO-178, you're going to have requirements and low-level tests that trace to all of those things. And having a lot of this boilerplate code can sometimes decrease legibility and increasing chance for introducing a defect during development, just with the amount of copy pasting that sometimes you have to do. But there are ways to get around that. In fact, if you can kind of make that work in your favor, the fact that all these EOPs kind of have similar bones and similar initializations, you can actually leverage that and have a lot of that kind of done for you through some automation that I'll talk about when I talk about some tooling. So one of the ways that we sped up the development process and lowered some of the risk of introducing a defect is we maintained our own kind of Hello World face application. So we called this MAS, the Modular Avionics Software Kit. So it's basically doing more or less the same thing that BALSA does, which is the kind of the publicly available example of face DOPs talking to each other. But instead of, unlike BALSA, it used all of our computing environment. So it was using our operating system profile. It was using RTSS. It was using just our kind of unique way that we initialize our UOPs. So it was much closer to what our development looked like. But it was basically doing the same thing with the same kind of function as BALSA did. But what we could do is that we could use it to test our entire face computing environment and our software stack. And then eventually that turned into a blueprint that we used to generate UOPs against that. Once we kind of realized every single one of our UOPs had, a common main and a common way we initialize things depending on how many messages it was sending and other UOPs that it was talking to. We made a generator for you plug in a USM and it automatically invokes your TSS type TS generation scripts and creates a bare bones application with no business logic. But all the UOP instantiation and injection is set up for you. So it's a form of code generation that is specific to face and specific to our own computing environment. So that sped up development significantly once we got that stood up. Talking about testing and simulation, when you're dealing with kind of high-level testing or integration testing or black box testing, when you are driving the software with representative external interfaces and verifying the behavior that happens afterwards, you have to know the ICD, know the on-the-wire format of that data that you're sending in, because the software is, you're not doing a white box test where you can like inject it with your exact data type. You're trying to drive it with on-the-wire message protocol. So the USM, your data model doesn't know exactly how those bytes are packed on the wire. It involves knowing exactly how the TPM formats that data. So we created a tool that basically combines our TSS message definition from the USM with the on-the-wire byte ordering of the TPM, and let us basically script a lot of our black box testing given the data model, and then it could drive the inputs and test the outputs of a face UOP just like it was a federated application not using a TSS. So here's kind of a run through of what our test environment looked like. We'd use our data modeling tool. We'd create a face data model and export an IDL file or turn that into an IDL file. And we would process that and turn it into what we called a face DB. And so it's kind of a more descriptive, byte-wise description of what the message actually looks like on the wire. And then we wrote a scripting language called SLAP, a program called SLAP, and that stands for software level automated parameters, I think. And that would actually, you could, byte by byte or message by message, automate the sending and checking of data into a face UOP, and then it would automatically run those tests and then verify the output. So it was a very good way to do automated black box testing once we had our UOP developed. One thing we also did a lot of analysis on was the airworthiness implications of applying an open standard, specifically the face standard. So there's a white paper out there about face conformance contributions to airworthiness, and a lot of the things that the face architecture requires you to do, like time and space partitioning, operating system profiles, defining your information flow between applications, that this is all required for face, but typically if you're writing higher DAL software, you're already going through the airworthiness process, and you're probably already going to have a lot of these applications. So face does go hand in hand because it was written to be kind of an avionics standard, but for high DAL software, you're already going to get a lot of that. On the flip side, there hasn't been as much analysis done on whether or not meeting face requirements is actually going to make airworthiness more difficult, and that's one of the things that we talked about a lot with our customer and internally. And one of the things that could prove difficult if not handled carefully by an integrator is that face drives a lot of UOPs to be written in C++. That's just kind of where the environment is right now. A lot of the UOPs that are available publicly, a lot of the TSSs provide applications or interfaces using the C++ bindings. There are some TSSs with C bindings out there. There are no publicly available ones, as far as I'm aware of, that have ADA bindings. And a lot of the UOPs that we got either as GFI or that we purchased from other companies, all written in C++. And C++ bindings tend to use heavy usage of virtual interfaces. And virtual interfaces can be difficult to test unless you're very familiar with airworthiness on C++ code. You have to exercise your polymorphic interfaces with all possible instances of the classes that they can be. So if you can't bound that in your code, then you have to do another layer of extra verification, and that's all described in the object-oriented supplement to DO 178. There's a lot of other examples in C++ that are some design patterns that can make it more difficult to certify software. I've listed a lot of those in the full text of the white paper. So the obvious answer to that would be to use a different language if you were worried about a very high DAO level application. So C and ADA are typically an answer to that. C++ is less used, but it is definitely used in the industry. But at the time that we were working on this, there is very few demonstrations of C and ADA, and especially publicly available, like a TSS that we could acquire that are in C and ADA. And so C code does help you a little bit. It doesn't have as many of the design patterns that can cause difficulties with low-level verification, but it still uses a lot of the dependency injection by passing around a lot of function pointers. So it still does incur that. And there are like I said, no publicly available TSS components that could use Ada that we could use. There was an application that we were working with that was written in Ada, and it had to use an Ada to C translation layer, then a C to C++ translation layer in order to get to the TSS, the C++ TSS that we had. There are also a plethora of conditions that can outright prevent the portability of a face component, and this is important, for down the road when an application is fielded or a platform is fielded, and potentially looking to upgrade a particular component or port a component that was developed for another platform onto another a modular open system. A lot of vendors of software that we work with that were just kind of getting into doing development against the FACE standard didn't understand a lot of these conditions that could prevent reuse into a system. And these are things that if you are really knowledgeable about FACE and you've done a lot of ports of airworthy components and things that have gone through certification, you probably already know a lot of this, that modifying any little bit of the code can trigger a recertification. However, it's important to realize that all these conditions are still there when porting in FACE software. So when you're looking at doing a port of a component into the integrator operating environment, don't skip on these factors that can happen. It is still, like, if all these things are equal and you can get the OEM to change a lot of these or align a lot of these with the original operating environment, then the integration does go very well and it can happen very quickly. And if it's minor modifications, potentially to some of the interfaces, and that original component has already gone through certification, it is a much smaller delta certification, to be sure. But if you're going to be bidding some kind of integration like this, then absolutely we recommend considering all these factors into how much recertification would be required. And one more thing is that in a lot of the TSS type TS generation, and even in our own code generation that I mentioned for creating the UOP code, the generated code for that application has to be verified per DO 178, just like everything else. And if you're using a code generation tool, that falls under DO 330, and it is if you're in a higher DAO application, it's TQL1, tool qualification level 1, which is the most demanding of the tool qualification levels, requires the most documentation verification of that tool. Because if you want to actually use that code in your application and not have to individually verify it with low-level requirements, low-level tests, then you are going to need to go to a TQL1 code generator. And currently there are no, at least that we're aware of, type TS TSS solutions that'll generate you a type TS that have a DO 330 certified code generator. And just for kind of to give an idea of the scale of the amount of code that can be generated for these, we had a little over 25 UOPs that we were dealing with, and our USM, when we put it into the code generation for the TSS, generated over 250,000 lines of code and about 3,000 files between all of the different injectable interfaces, the headers, and all that. So all that code, if you don't have a DO 330 certified code generator and you need to go through DO 178 certification, all have to be verified individually. So, our advice would be that if you're doing a BOE or scoping the work that's required to do development for an open system, you definitely have to factor in the amount of generated code and whether or not you have a qualified tool to do so. And the last thing I'll say is one thing we really took home from this program is that the OSBD event, it was very, very eye-opening, and having a third party come in and do this verification. That's really the one true test to see if a system is open, is to have a representative event happen where somebody who is not part of the original development, is not part of the integrator team, comes in with a completely different component and ingests all of the artifacts that we had developed, all of our documentation, all of our data models, all of that kind of stuff, and actually add a component to our system or plug in a new component to our system and get it to talk to our existing software, or even replace one of our components like our display altogether. Those definitely reveal things about our system that were not open and were not compatible with software, even though it should have been. And sometimes that was an issue on our side, and we had to go and verify that. But we got to learn that before our system was fielded. And even though the program was shut down earlier this year, we still had those lessons learned. Is that okay? Next time, let's do this way and that. And then when we did that, we adapted it. The next OSVD event came along, and then it wasn't a problem anymore. So there's still a lot of learning that can happen in this, and it wasn't cheap to do an OSVD event. Obviously, you're having to coordinate between all these different parties and the third-party developer and spend a lot of time bringing them in. But running these events for a very large-scale open system platform is definitely required. And if you can't do an OSVD event, if that's not part of your program, definitely set aside time to do a self-evaluation. The DoD has promised to come out with timelines, milestone documentation for how to verify against a MOSA, but they're not there yet. So everybody kind of has to self-verify or run an open systems verification event. So we list in the white paper a couple of example test cases that you can run against your own system in order to verify if the system is actually going to be open and if you can port additional software coming in. And so if in the white paper, there are some examples, you can use that as kind of a template if you're going to do kind of a self-verification or self-attestation of the openness of a system. So the takeaway from this paper that we're hoping for people to have is that overall, to realize the value of MOSA on a larger scale, that in general, down the road, a successful application of MOSA is going to save a lot of time, money, and effort for the system or the platform over the lifetime of the platform. But that initial development is still going to take about as long or even longer than a typical development of a similar component, because you're having to make sure you're applying all these standards, not just on the service level, but correctly and in a way that is well documented and easy for it to be leveraged down the road. And if you're an integrator and you're looking at this saying, okay, well then why this is going to take a lot of extra time, why should I be bidding on this when it's just going to be a lot of extra development? The open standards can benefit the integrator as well and the developer of the software. Because we're using a lot of open standards, all the developments for all these UOPs starts to actually look pretty similar from program to program. And so you can develop a tool suite and a verification suite, and a lot of the same tooling that you would normally use in an on-target avionics platform, just applying all those open standards and having that little extra work done to really set up your harnessing and your verification pipeline, so that now that every one of your programs is starting to use maybe the same open standard, then you actually start to save time, because you can save a lot of that upfront boilerplate work in order to get your computing environment stood up. So don't sleep on setting up your ecosystem of software tools, your verification procedures, and your ways to verify your own open system. And that way, when you bid on new programs and when your customer comes and evaluates you on whether or not your system is actually open, you have a way to prove that to them, and you have a way to test that against yourself. And then that can build up better business down the road when they come back and say, wow, that open system verification or that open system development, they definitely knew what they were doing, and it took half the time of other people who have built up the system. So it still definitely benefits to create all that stuff within your own development team and for your product lines that are going to be applying these standards. All right, well, thank you everybody for your attention. I think I saw a couple of questions in the chat. Let me see if I can read through those.
There are. The first question is, and this is in the chat, not in the Q&A, is, have you seen development time loss associated with upgrading FACE for SOSA standards, like upgrading FACE 2 to 3? follow-on question to that is, how does that compare to development time in a federated approach?
That's a good question. Yes, it did take time to do a port of older standards to new standards. We had a couple components that were developed against an older version of the FACE standard, or even updating a data model to the new version of the SDM. That definitely took time. Now, did that take more time than a federated approach? I don't think so in that regard. Like, once you've done a lot of that initial development, if you are updating your FACE standard, depending on the tool chain that you're using, a lot of it just involves changing the data model. But if you're totally ripping out and changing to a new version of the standard, like going from 2 to 3 is a fairly significant process. But it's kind of the same as changing to a brand new ICD. Of, for example, you changed out your EGI or something like that in your system. Going to a brand new ICD, it's about that same level of work. It's just kind of where that work is being spent. And if you have done it a couple times, it goes faster and faster every time.
Okay, the next thing in the chat is actually a comment. It's not truly a question. It says higher DAL levels require you to test the source code, not just the model with a DO-330 qualified tool. But this seems to be somewhat dependent on the opinion of your DER.
Yeah, I mean, that is definitely a true statement. I don't have as much experience with DAL-A development, especially when you get down to object code too. That's another thing to consider. Is even if you have a qualified tool, you probably still have to test and verify a lot of the object code that it generates. So yeah, it does vary from DER to DER about how trusting they are of your code generation. And I think that's probably another topic for those who have experience with a code generator tool. Like if you're dealing with like a Presagius or an ANSYS generation tool and generating code for a TSS, like a lot of the TSS tools do. I think that's something that definitely requires consideration, is how much verification is required beyond just the tool qualification.
Okay, and the last question is, can certification be done on targeted components only?
I'm not sure what that means on just targeted. Okay, like I'm going to assume that you mean like a recertification on targeted components. That is very specific to the program office and SRD or your DER that you're working with. But in general, yes, because DO-178 requires or allows you to use to reuse certain components from previous development. So if you have a bunch of different software components and you're bringing them forward to do a recertification, it all gets described in your plan for software aspect of certification. You're saying, I'm going to reuse this component, I'm going to use this component which has already been certified with this delta. And if your DER agrees to that, then you're good. You can to perform a delta certification just to the things that have changed. And so if you have a platform that everything has been certified, and let's say you're just changing out a couple of UOPs, one of the benefits that using the open standard is, and modular code and modular products, is that you've isolated the interfaces to each component. So you can do a delta certification just for one of those targeted components that's been changed. It's just you have to be very careful about quantifying the amount that has to change, because sometimes changing something is even as seemingly simple as like the TSS that you're using can really change a lot of the actual source code, and the delta certification might be actually a lot more work than you might think.
All right, thank you very much, Trevor. That was excellent.
All right, yeah, thanks everybody for your time. You can email me at the link you see here if you have any other questions.